All right, we are talking chapter 7, which is energy and thermodynamics. And last time we got into a couple things. We got into change in enthalpy, and that's delta H. And that can be calculated by taking the delta H of our products minus the delta H of our reactants. And delta H is very commonly the way that we calculate the heat, excuse me, the heat associated with the reaction. We do need to take into account the coefficients. So if we have coefficients, when we look up the values in the table, we would need to do our delta H of the reaction would be the 4 times the delta H value of C in this case, minus 2 times the delta H value of A, and that would be added to 3 times the delta H value of B. You want to make sure you look up things in the correct sort of state. You also got to, again, take into account that coefficient when you're calculating them. And a reminder that the delta H, if it is negative, means it's an exothermic process. And if the delta H is a positive value, that would be an endothermic process. And we saw some energy diagrams, I think, as well. And here we have our reactants higher in energy than our products, which means overall this is going to be an exothermic process as energy is going to be given off. That hill that the reactants has to climb to get to their side is known as the activation energy, and that's the minimum amount of energy required for a reaction to take place. For our endothermic type of diagram, it looks a little bit different. Reactants are lower in energy than the products. So energy has to be kind of put in, and it's endothermic. And again, this would be our activation energy in this case. Remember, it is the difference between the energy of the reactants and the energy of the products that is the delta H that we calculated. And again, we do get a negative number for exothermic because, as you can see on the diagram here, our products is a smaller energy value than our reactants. So we end up with a negative value. And that's opposite when we look at our endothermic here. Our reactants are actually a lower value than our products. So when you subtract those two, you will get a positive value there for your delta H of that reaction. We also got into specific heat and specific heat capacity. Q equals ms delta T. Q is heat or energy and has units of joules or calories. M is mass, which has units of grams. S is the specific heat capacity, which is joules per gram per degree Celsius, or calories per gram per degree Celsius. Again, people oftentimes get these two confused, but the specific heat capacity has all three of those units. And as we talked about last time, the change in temperature, one of the few things that you could leave in degrees Celsius here, but also really important to make sure that you take the final temperature minus the initial temperature. As we talked about last time, that is essentially going to be the one thing in this equation that will allow you to either get a positive value for Q or a negative value for Q. And if you do get a negative value for Q, that also means it's an exothermic process. And if you get a positive value, it is an endothermic process. Any questions on that stuff from last time? All right, then let's talk about another sort of aspect of this, and that is the idea when we sort of transfer heat from one object to the next. As we've been talking about, we sort of assume that it's this kind of perfect transfer of energy. So whatever amount of energy one thing sort of loses will be the same amount of energy that somebody else gains. So for example, here, if we here. So for example, if we took a piece of metal, and we'll just say the mass of the metal is 95 grams. We say we heated this metal up to about 99 degrees Celsius. And we take a container of water here. And let's just say we have the mass of the water is 110 grams. The initial temperature of the water is 28 degrees Celsius. So when I put this piece of metal into this water, what is going to happen, as we talked about, is heat does flow from hot to cold. So the hot piece of metal will release all its energy into the water, and the water is going to pick up all that energy from the metal. The end result of that is we will see the water's temperature increase. We'll just call it 32 degrees Celsius. We also know from this sort of situation that eventually this piece of metal here is going to be sitting in that water, and it will come to rest at pretty much equilibrium with the temperature of the water. So we will also know the final temperature of the metal will be 32 degrees Celsius. Again, it should be the final temperature of the water as it's basically sitting in there. So if we want to know something like what is the specific heat capacity of the metal, we could use this sort of process here very simply to figure it out. And the reason we could do that is we always have sort of the value there, specific heat of liquid water, which is 4.184 joules per gram per degree Celsius. So if we think about the specific heat equation and we think about it for water, we have the mass, we have the specific heat capacity, and we do have the change in temperature, which means in this particular case, we could figure out how much energy that the water gained from the metal. And if we do that here, Q of the water would be in my made up numbers here, 110, 4.184 joules per gram per degree Celsius. Final temperature here, 32 minus 28 degrees Celsius. And that's going to get us here. I guess somewhere like 1841, we'll just call it joules. At this point, the grams will cancel, the degrees Celsius will cancel, going to leave us in joules. We see that, as we would expect here, because the piece of metal was much hotter than the water gained that much energy. It's endothermic for the water as it picked up all that energy, and we did get a positive value here for our metal. Now, one of the things that we do know is all the energy that the water gained had to come from really the piece of metal. So we could have this relationship between, for example, the metal and the water in this case, that Q of the metal will equal negative Q of the water. It will be the same number, but the sign will be different because for the metal in this case, it is exothermic. So the Q of the metal in this case would be the same number, but it'd be negative 1841 joules, as it is, again, the metal releasing the energy. So by using the water here, we're now able to figure out how much energy was actually lost by the metal. And we can actually go back into our specific heat equation here. And we can now solve for the specific heat capacity for our metal. And that would equal Q of the metal divided by m delta T. And if we put that in there, negative 1841 joules. Our mass of our metal, 95 grams. And again, it's really important at this point to also remember you guys still do final minus initial. And for the metal here, our final is 32. Our initial is 99. The importance of that is this is going to give you a negative number, which will go good with that negative number to turn that into a positive number. So again, you need to make sure that you kind of pick up the negative sign correctly. And if you do that there, you will end up with something here. Something like 0.289 joules per gram per degree Celsius. Not bad on a made-up problem. So this is a very common sort of procedure that we can use, basically the change that happens with water. And by figuring out, for example, in this situation, how much energy that the water gained, we could then figure out how much was lost by whatever went into the water, and we can use that information to solve for what we're looking for. Any questions on that there? And that is what this equation here says. The total amount of heat transfer is equal to 0. and that is the specific heat capacity of the water and the specific heat capacity of the metal. If you do this, remember though that you need to move one of these to the other side, and that will also change the sign if you set them equal to each other. So again, you got to have that negative sort of changing the sign in this to help you solve for it. All right, so why don't you try one here? You got a 110-gram sample of a metal at 55 degrees Celsius, raises the temperature of 150 milliliters of water from 23 to 25.5. What is the specific? Let's take a look. So we got a 110-gram sample of a metal. It rises the temperature of 150 milliliters of water, and we're looking at specific heat capacity of the metal. So kind of a similar situation to what we were just talking about. We have basically some water here, and we have 150 milliliters of it. It is at an initial temperature of 23 degrees Celsius. It goes to a final temperature of 25.5 degrees Celsius. When the metal goes in, we always know specific heat capacity of liquid water, 4.184 joules per gram per degree Celsius. For our metal over here, we got 110 grams, which is our mass. We got the initial temperature here of 55.5 degrees Celsius. Once again, is going to go for a swim. In this particular case, as we talked about previously, our metal is hotter or a higher temperature than our water. So again, it is going to be the one releasing the energy into the water in this case. That means that the metal will end up at the same final temperature as the water, which would be 25.5 degrees Celsius. And we are looking for the specific heat capacity here for our metal. We're also missing Q for our metal, and we would be able to get Q really from the water information. So again, here we have pretty much everything we need for the water to figure out, once again, in this particular case, how much energy the water should gain. We're not given the mass of the water, but we are given the volume. So this is a situation where if you needed to, you could use the density of water. And again, when you pretty much need to use the density of water, 1 gram per milliliter is the choice there. And that's going to give me 150 grams of water. So now we could do this for our water here. We'll go with 150 grams of water. Our specific heat capacity, 4.184 joules per gram per degree Celsius. Final temperature here, 25.5 minus 23 degrees Celsius. And that will get us here 150 times 4.184 times 25.5 minus 23. Looks like something like 1,569 joules. That again is going to be the information we're going to use to relate it back to the metal. As we just talked about, pretty much all that energy came from the metal, which means that is, again, the same value for the metal in terms of Q. But again, the sign will be different because it's exothermic in this case. So once again, you can use that relationship of Q of the metal equals minus Q of the water. And that would mean that for our Q of the metal here, it's going to be, again, the exact same number, except a negative version in this case, because it's exothermic. With that, we now have pretty much everything we need for our metal. So our Q of our metal here going to be ms delta T. The S is going to be Q of our metal divided by m delta T, negative 1569 joules divided by the mass of the metal, 110 grams. And again, we want to go final minus initial here in terms of the temperature of the metal, 25.5 minus 55.5. Once again, that's going to give us the negative. We need to get rid of that negative there. And that will get us here 1569 divided by 110 divided by 25.5 minus 55.5. And it looks like we will end up with 0.475 joules per gram per degree Celsius, as none of these units cancel. Any questions on that? Now, again, in these couple examples we did, the water was gaining the energy, but it is possible, obviously, to go the other way around, that the metal, for example, that you put in there or something, or whatever objects you put in there might be actually be colder than the water's temperature. So the energy transfer could go in the opposite direction as well. Any questions on specific heat capacity here? All right. Now let's talk a little bit about energy and nutrition, which I think we touched upon the other day. Again, when we talk about calories, which is a unit of energy, there are capital calories, which are nutritional calories, and they are equal to 1,000 of the little calories. So when you have one capital calorie, that's 1,000 of the lowercase calories, or 1 kilocalorie. Calorimeter is an apparatus that's used to determine the number of calories in food. This is what is sometimes referred to as a bomb calorimeter. It's a pretty isolated container. It pretty much has water inside. You can put your food sample over here, some oxygen, some wires to ignite it. And basically, it's really the same concept that we've been talking about, that you could set it on fire, basically. As obviously the food burns, it's going to transfer the heat and energy to the surrounding waters. You can find the change in the temperature of the surrounding waters and actually just do a simple calculation like we just did there with the specific heat, and you can figure out how many calories, nutritional calories, were in your food. Now, when you look at, for example, a nutrition label, there oftentimes are three categories of a sort of food there. There's carbohydrates, there's fats, and proteins. And if you look at a nutritional label, oftentimes they'll tell you how many grams of each of those are in whatever you're eating. And each of those has what's referred to as a caloric content or caloric value. And for carbohydrates and proteins, that's 4 kilocalories per gram. And for fat, that's 9 kilocalories per gram. And you could actually calculate, for example, where it says total calories in your servings. That is how you could basically do that. They can figure out the caloric value based on that. You take the caloric values of the carbohydrates, fats, and protein, and times it by the grams of each of them, add them together, and that'll give you your calories. Now, another very common method that we use to do these type of experiments in the laboratory is actually just some styrofoam coffee cups. Styrofoam coffee cups are pretty good. They're well insulated, and it allows these experiments to work really, really well. And you could do these sort of experiments because all you need basically is some coffee cups and a thermometer, and you can follow the change in temperature of the water. And you could actually calculate the Q value there using the equation we've used before. And if you do this under constant pressure conditions, which typically you do, the delta H of the reaction there will equal Q under that situation. So you could actually calculate the change in enthalpy for a reaction. We could do this type of experiment like we did in those examples where maybe you toss a hot piece of metal or some type of metal into water. You could also do these type of experiments really well with actual just regular reactions. So you can mix like acid and bases together in the coffee cup and again follow the change in temperature. And you can do that a lot of times because solutions are aqueous, and water is basically a lot of times the solvent that is used. And even though, for example, you are not using the acid or base specific heat capacity, you could use the specific heat capacity of water, liquid water, and usually will come out pretty close because it's mainly an aqueous type solution. So super common way to figure out the Q of the reaction, also the delta H of the reaction. You could take like HCl and put some magnesium in there, let it do its reaction, and follow the change in temperature. All right. So, for example, if we have 1 ounce serving of oat bran cereal with some milk, and it contains 22 carbohydrates, 7 grams of fat, and 10 grams of proteins. If you eat 2 servings of oat bran for breakfast, how many kilocalories did you obtain? So as I mentioned before, these are typically values, for example, you can find on the back of nutrition labels on food. So if we take, for example, here 22 grams of carbohydrates, and we times it by the caloric value for carbohydrates, which is 4 kilocalories per gram, we take our 7 grams of fat and times that by its caloric value of 9 kilocalories per gram. And we take our protein here and times it by its caloric value of 4 kilocalories per gram. We'll end up with 88 kilocalories there. We'll have our 63 kilocalories there and our 40 kilocalories there. And if we add all these together here, 40 plus 63 plus 88, comes to about 191 kilocalories. And since we're having 2 servings, we could times that by 2, and we would have something like 382 kilocalories, which is 382 nutritional calories in this particular case. So once again, that is basically how, like I said before, they get these sort of calories per serving sort of value in a sense off of those nutrition labels. In my experience, oftentimes they do round down, so it's less calories than you would normally get. But that again is how you get that. Any questions on that there? Okay, the next thing we're going to talk about then is the idea of Hess's law. And the idea of Hess's law is the idea that not all reactions occur in a one-step fashion. So not all reactions will go from reactants to products in sort of one move. Sometimes the overall reaction is a result of multiple individual reactions happening, and we can basically add those reactions together. Now, when we look at a reaction that has a delta H value together, I think we might have talked about it. In case we didn't, let's just talk about it for a second here. When we have an equation like A plus B goes to C, and we'll just say that delta H here is 10 kilojoules. When we manipulate this equation, it does affect the delta H value. So for example, if we wanted to reverse this reaction, that would give us C goes to A plus B. And what that does to the delta H value is it actually changes the sign. So instead of positive 10 kilojoules, this then would become basically negative 10 kilojoules. And the idea behind that is when we calculate delta H is products minus reactants. So when you reverse the reaction, your products become your reactants, reactants become your products. So you get the same value, but again, the sign changes because of doing that. Now, sometimes we may have to, for example, multiply an equation by a common number. And if we do that, you get 2A plus 2B goes to 2C. And how that affects the delta H value is you would actually multiply the delta H value by that 2. And that would give you 20 kilojoules. And the last thing that we typically do here is if we needed to, for example, divide by a common number. So let's just say we wanted to divide this guy by 2. That will put us back to our original equation. And our delta H would then be 20 kilojoules divided by 2 are 10 kilojoules. So these are really 4 different ways that we can manipulate an equation that has a delta H value. And again, it is very different than what we do with equilibrium constant values when we add equations together. So this is more multiplying, dividing, and changing the sign. Any questions on that? So this is really important for something like Hess's law, which, as I mentioned, is this idea that if you sum up a bunch of individual reactions to get like an overall reaction, you basically should just add up all the individual delta H values. Now, sometimes it may require you to manipulate each of the individual equations, like we just talked about, to get what you're looking for. So, for example, here, if we were to add these two reactions together, much like normal, anything that's on opposite sides of the arrows will cancel or reduce down. So here the water cancels out in the gas phase, and that leaves us our water, H2 plus our half, O2 goes to our water. In this case, we really didn't do anything to the delta H values, so all we would do is add these guys together, and that would give us our delta H of the overall reaction, which would be minus 285.8. So why don't you try one here? The desired equation is the one we're looking for up on top. Okay, let's take a look. And when you're doing these sort of Hess's Law problems, sometimes you have just two equations, sometimes you have multiple equations, three, four of them. Probably the simplest approach is to just try to make sure you get everybody on the correct side and make sure you have everything there in terms of how many you need. So if I was to do this first one here, I just have carbon here on the left, and I see carbons in this equation, it's on the left, and there's just one, and that is what I need. So I'm really not going to do anything with this equation at this point. I could also look at, for example, CO2 here, which is on the right, and I see CO2 over here is on the right, and there's one in each of them. So really for this first one, I don't really have to do much with any of those equations other than add them together. And when I add them together, the CO is going to cancel. That will leave me a C on the left. Half O2 and half O2 gives me a whole O2 and a CO2. And once again, in this case, for the first one, since I didn't really do anything to it, all I'm going to simply do is just add those numbers together. So minus 110 plus minus 283 going to give us a negative 393 kilojoules in this particular case. First off, any questions on the first one here? All right, then let's take a look at the second one here, which we do need to do some things to it, I think. All right, so I'm going to take the same approach here for the second one. And on the second one here, I actually have CO2 on the left-hand side. And once again, this is the only equation where CO2 is in it, and it's on the right-hand side. So I know for sure I need to reverse it. In addition, I don't need just one CO2, but I need two of them. So in addition to reversing it, I also need to multiply it by 2. So that is what I'm going to do here for the second equation. We're going to go with, we're going to reverse it first. And I'm also going to multiply it by 2, which would give me a 2 there, a 2 there, and a 1 there. Now, because I reverse that equation, what's going to happen to the sign is it will become positive 283. And I also multiplied it by 2, which means I do need to multiply the H value there by 2. I'm going to do the same thing here for the next one, which is carbon. It's on the right-hand side here. Over here, it's on the left-hand side. So once again, I am going to have to reverse that equation as well. So that would give me CO goes to C plus O2. I also need not one carbon, but 2. So once again, I will have to multiply this by 2 as well. And again, because I reversed it and multiplied by 2, we're going to go with a plus 110 on that for the reverse and a multiplying by 2. That's going to give me, hopefully, the reaction I'm looking for, which is these guys are going to cancel. 2CO2 goes to 2C plus 2O2. Delta H in this case will now be just adding these guys together. And that's going to get me 283 times 2 plus 110 times 2. Looks like 786 kilojoules in this case. Any questions on that one there? All right, let's take a look at another one then. Let's see here. So what is the delta H for this reaction based on the 2 that are given? So take a few moments there to see what you come up with. I see SO2 here on the left. This is my only SO2. It's on the right. And I do need to reverse it because it needs to be over there. I also just need one of them. So I know really on top one here, I'm probably just going to reverse it. So SO2 goes to S plus O2. Once again, since I reversed the reaction, that's going to change the sign here of my delta H. For the next one here, looking at the SO3, I do have it on the right, and I do need it on the right over here, except that I only need one, and I do have two of them here in this equation on the bottom. So I will need to divide this guy by 2, and if I divide that by 2, that's going to give me an S plus 3 over 2O2 goes to just one SO3. And in this case, I divided by 2, which means 792 kilojoules divided by 2 will give me my delta H for that equation there. And that's going to be 396, it looks like. So if I've done this correctly, we should end up with what we're looking for. So those are going to cancel, and that's going to leave me an SO2 on the left. Plus, there is 1 here, which is 2 over 2, minus 3 over 2 leaves me a half of O2, gives me an SO3. So I did get the correct equation there. That means my delta H will be adding these guys together, and that's going to give me a 297 plus a negative 396. Looks like a negative 99 kilojoules, meaning it is exothermic, this reaction, yeah? Any questions on that there? So a question on Hess's law. So again, could have multiple equations, just try to get everybody to the right side and keep track of what you did. So as we've talked about, heat is the flow of energy due to temperature difference and the transfer of thermal energy between two objects that are at different temperatures. The change in internal energy, which is delta E, is the heat, or Q, added to the system plus the work. By convention, energy, heat, and work added to the system is positive and removed is negative. So again, some of the same ideas, sort of like exothermic and endothermic. Endothermic sort of absorbing. We get that positive values here. So same idea with sort of our change in internal energy. If it's positive or negative, sort of the same idea, kind of giving off or absorbing the energy. Now, what we're going to talk about in the next chapter, the rest of thermodynamics, is this idea of spontaneity and a spontaneous sort of reaction. And one of the processes that sort of helps something become spontaneous or helps some type of reaction become spontaneous is what is sometimes referred to as this sort of energy spread. And as heat flows from high to low temperature, it spreads out. And that's really good for things being spontaneous. This kind of flow of energy doing it. As we will see, again, sometimes people think exothermic is always sort of necessary for a reaction to be spontaneous. And it's not necessarily true. There are a lot of reactions that are endothermic that are spontaneous as well. But this energy flow and matter spread are things that really help things become spontaneous. So for example, if you just think about if you dissolve some salt in water, what happens is that salt, which is before you dissolve it, pretty tightly packed together, all in one sort of cube, if you will. But when it does so, what it does is it starts to dissolve and it breaks apart into its ions, and those ions spread out over the solution, and you make that solution. And again, it helps the spread of the matter and also energy associated with it. Any questions on that there? All right, well, that is, they say, chapter 7 and so forth. All right, I am good for today.